Speech recognition is an interdisciplinary subfield of computer science and computational linguistics that develops methodologies and technologies that enable the recognition and translation of spoken language into text by computers. It is also known as automatic speech recognition, ASR, computer speech recognition or speech-to-text, STT. It incorporates knowledge and research in the computer science, linguistics and computer engineering fields. The reverse process is speech synthesis. Some speech recognition systems require training, also called enrollment, where an individual speaker reads text or isolated vocabulary into the system. The system analyzes the person's specific voice and uses it to fine-tune the recognition of that person's speech, resulting in increased accuracy. Systems that do not use training are called speaker-independent systems. Systems that use training are called speaker-dependent. Speech recognition applications include voice user interfaces such as voice dialing, e.g. call home, call routing, e.g. I would like to make a collect call, demotic appliance control, search keywords, e.g. find a podcast where particular words were spoken, simple data entry, example entering a credit card number, preparation of structured documents, e.g. a radiology report, determining speaker characteristics, speech-to-text processing, example word processors or emails, and aircraft. Usually termed direct voice input. Automatic pronunciation assessment is used in education such as for spoken language learning. The term voice recognition or speaker identification refers to identifying the speaker, rather than what they are saying. Recognizing the speaker can simplify the task of translating speech in systems that have been trained on a specific person's voice, or it can be used to authenticate or verify the identity of a speaker as part of a security process. From the technology perspective, speech recognition has a long history with several waves of major innovations. Most recently, the field has benefited from advances in deep learning and big data. The advances are evidenced not only by the surge of academic papers published in the field, but more importantly by the worldwide industry adoption of a variety of deep learning methods in designing and deploying speech recognition systems. Applications. Typically a manual control input, for example by means of a finger control on the steering wheel, enables the speech recognition system, and this is signaled to the driver by an audio prompt. Following the audio prompt, the system has a listening window during which it may accept a speech input for recognition. Simple voice commands may be used to initiate phone calls, select radio stations, or play music from a compatible smartphone, MP3 player, or music-loaded flash drive. Voice recognition capabilities vary between car make and model. Some of the most recent car models offer natural language speech recognition in place of a fixed set of commands, allowing the driver to use full sentences and common phrases. With such systems there is, therefore, no need for the user to memorize a set of fixed command words. Automatic pronunciation assessment is the use of speech recognition to verify the correctness of pronounced speech, as distinguished from manual assessment by an instructor or proctor. Also called speech verification, pronunciation evaluation, and pronunciation scoring, the main application of this technology is computer-aided pronunciation teaching, CAPT, when combined with computer-aided instruction for computer-assisted language learning, CALL, speech remediation, or accent reduction. Pronunciation assessment does not determine unknown speech, as in dictation or automatic transcription, but instead, knowing the expected word, s, in advance, it attempts to verify the correctness of the learner's pronunciation and ideally their intelligibility to listeners, sometimes along with often inconsequential prosody such as intonation, pitch, tempo, rhythm, and stress. Pronunciation assessment is also used in reading tutoring, for example in products such as Microsoft Teams, and from Amiro Learning. Automatic pronunciation assessment can also be used to help diagnose and treat speech disorders such as apraxia. Assessing authentic listener intelligibility is essential for avoiding inaccuracies from accent bias, especially in high-stakes assessments, from words with multiple correct pronunciations, and from phoneme coding errors in machine-readable pronunciation dictionaries. In 2022, researchers found that some newer speech-to-text systems, based on end-to-end reinforcement learning to map audio signals directly into words, produce word and phrase confidence scores very closely correlated with genuine listener intelligibility. In the Common European Framework of Reference for Languages, CEFR, assessment criteria for overall phonological control, intelligibility outweighs formally correct pronunciation at all levels. In the healthcare sector, speech recognition can be implemented in front-end or back-end of the medical documentation process. Front-end speech recognition is where the provider dictates into a speech recognition engine, the recognized words are displayed as they are spoken, and the dictator is responsible for editing and signing off on the document. Back-end or deferred speech recognition is where the provider dictates into a digital dictation system, the voice is routed through a speech recognition machine and the recognized draft document is routed along with the original voice file to the editor, where the draft is edited and report finalized. Deferred speech recognition is widely used in the industry currently. One of the major issues relating to the use of speech recognition in healthcare is that the American Recovery and Reinvestment Act of 2009, ARA, provides for substantial financial benefits to physicians who utilize an EMR according to meaningful use standards. These standards require that a substantial amount of data be maintained by the EMR, now more commonly referred to as an electronic health record or EHR. The use of speech recognition is more naturally suited to the generation of narrative text, as part of a radiology/pathology interpretation, progress note or discharge summary. The ergonomic gains of using speech recognition to enter structured discrete data, example numeric values or codes from a list or a controlled vocabulary, are relatively minimal for people who are sighted and who can operate a keyboard and mouse. A more significant issue is that most EHRs have not been expressly tailored to take advantage of voice recognition capabilities. A large part of the clinician's interaction with the EHR involves navigation through the user interface using menus and tab/button clicks, and is heavily dependent on keyboard and mouse. Voice-based navigation provides only modest ergonomic benefits. By contrast, many highly customized systems for radiology or pathology dictation implement voice macros, where the use of certain phrases, example normal report, will automatically fill in a large number of default values and or generate boilerplate, which will vary with the type of the exam, example a chest X-ray versus a gastrointestinal contrast series for a radiology system. Prolonged use of speech recognition software in conjunction with word processors has shown benefits to short-term memory re-strengthening in brain AVM patients who have been treated with resection. Further research needs to be conducted to determine cognitive benefits for individuals whose AVMs have been treated using radiologic techniques. Substantial efforts have been devoted in the last decade to the test and evaluation of speech recognition in fighter aircraft. Of particular note have been the U.S. program in speech recognition for the Advanced Fighter Technology Integration, AFTI/F-16 aircraft, F-16 Vista, the program in France for Mirage aircraft, and other programs in the UK dealing with a variety of aircraft platforms. In these programs, speech recognizers have been operated successfully in fighter aircraft, with applications including setting radio frequencies, commanding an autopilot system, setting steer point coordinates and weapons release parameters, and controlling flight display. Working with Swedish pilots flying in the JAS-39 Gripen cockpit, Englund, 2004, found recognition deteriorated with increasing G-loads. The report also concluded that adaptation greatly improved the results in all cases and that the introduction of models for breathing was shown to improve recognition scores significantly. Contrary to what might have been expected, no effects of the broken English of the speakers were found. It was evident that spontaneous speech caused problems for the recognizer, as might have been expected. A restricted vocabulary, and above all, a proper syntax, could thus be expected to improve recognition accuracy substantially. The Eurofighter Typhoon, currently in service with the UK RAF, employs a speaker-dependent system, requiring each pilot to create a template. The system is not used for any safety-critical or weapon-critical tasks, such as weapon release or lowering of the undercarriage, but is used for a wide range of other cockpit functions. Voice commands are confirmed by visual and/or oral feedback. The system is seen as a major design feature in the reduction of pilot workload, and even allows the pilot to assign targets to his aircraft with 2 simple voice commands or to any of his wingmen with only 5 commands. Speaker-independent systems are also being developed and are under test for the F-35 Lightning II, JSF, and the Alenia Air Macchi M346 Master Lead-In Fighter Trainer. These systems have produced word accuracy scores in excess of 98%. The problems of achieving high recognition accuracy under stress and noise are particularly relevant in the helicopter environment as well as in the jet fighter environment. The acoustic noise problem is actually more severe in the helicopter environment, not only because of the high noise levels but also because the helicopter pilot, in general, does not wear a face mask, which would reduce acoustic noise in the microphone. Substantial test and evaluation programs have been carried out in the past decade in speech recognition systems applications in helicopters, notably by the U.S. Army Avionics Research and Development Activity, AVRADA, and by the Royal Aerospace Establishment, RAE, in the UK. Work in France has included speech recognition in the Puma helicopter. There has also been much useful work in Canada. Results have been encouraging, and voice applications have included control of communication radios, setting of navigation systems, and control of an automated target handover system. As in fighter applications, the overriding issue for voice in helicopters is the impact on pilot effectiveness. Encouraging results are reported for the AVRADA tests, although these represent only a feasibility demonstration in a test environment. Much remains to be done both in speech recognition and in overall speech technology in order to consistently achieve performance improvements in operational settings. Training for air traffic controllers, ATC, represents an excellent application for speech recognition systems. Many ATC training systems currently require a person to act as a pseudo-pilot, engaging in a voice dialogue with the trainee controller, which simulates the dialogue that the controller would have to conduct with pilots in a real ATC situation. Speech recognition and synthesis techniques offer the potential to eliminate the need for a person to act as a pseudo-pilot, thus reducing training and support personnel. In theory, air controller tasks are also characterized by highly structured speech as the primary output of the controller, hence reducing the difficulty of the speech recognition task should be possible. In practice, this is rarely the case. The FAA Document 7110.65 details the phrases that should be used by air traffic controllers. While this document gives less than 150 examples of such phrases, the number of phrases supported by one of the simulation vendor's speech recognition systems is in excess of 500,000. The U.S. Air Force, USMC, U.S. Army, U.S. Navy, and FAA as well as a number of international ATC training organizations such as the Royal Australian Air Force and civil aviation authorities in Italy, Brazil, and Canada are currently using ATC simulators with speech recognition from a number of different vendors. ASR is now commonplace in the field of telephony and is becoming more widespread in the field of computer gaming and simulation. In telephony systems, ASR is now being predominantly used in contact centers by integrating it with IVR systems. Despite the high level of integration with word processing in general personal computing, in the field of document production, ASR has not seen the expected increases in use. The improvement of mobile processor speeds has made speech recognition practical in smartphones. Speech is used mostly as a part of a user interface, for creating predefined or custom speech commands. People with disabilities can benefit from speech recognition programs. For individuals that are deaf or hard of hearing, speech recognition software is used to automatically generate a closed captioning of conversations such as discussions in conference rooms, classroom lectures, and/or religious services. Students who are blind, see blindness and education, or have very low vision can benefit from using the technology to convey words and then hear the computer recite them, as well as use a computer by commanding with their voice, instead of having to look at the screen and keyboard. Students who are physically disabled have a repetitive strain injury/other injuries to the upper extremities can be relieved from having to worry about handwriting, typing, or working with scribe on school assignments by using speech-to-text programs. They can also utilize speech recognition technology to enjoy searching the internet or using a computer at home without having to physically operate a mouse and keyboard. Speech recognition can allow students with learning disabilities to become better writers. By saying the words aloud, they can increase the fluidity of their writing, and be alleviated of concerns regarding spelling, punctuation, and other mechanics of writing. Also, see learning disability. The use of voice recognition software, in conjunction with a digital audio recorder and a personal computer running word processing software, has proven to be positive for restoring damaged short-term memory capacity in stroke and craniotomy individuals. Speech recognition is also very useful for people who have difficulty using their hands, ranging from mild repetitive stress injuries to involved disabilities that preclude using conventional computer input devices. In fact, people who used the keyboard a lot and developed RSI became an urgent early market for speech recognition. Speech recognition is used in deaf telephony, such as voicemail to text, relay services, and caption telephone. Individuals with learning disabilities who have problems with thought-to-paper communication, essentially they think of an idea but it is processed incorrectly, causing it to end up differently on paper, can possibly benefit from the software, but the technology is not bug-proof. Also, the whole idea of speak-to-text can be hard for intellectually disabled persons due to the fact that it is rare that anyone tries to learn the technology to teach the person with the disability. This type of technology can help those with dyslexia, but other disabilities are still in question. The effectiveness of the product is the problem that is hindering it from being effective. Although a kid may be able to say a word, depending on how clear they say it, the technology may think they are saying another word and input the wrong one, giving them more work to fix, causing them to have to take more time with fixing the wrong word. Further applications: aerospace, e.g. space exploration, spacecraft, etc. NASA's Mars Polar Lander used speech recognition technology from sensory incorporated in the Mars microphone on the lander. Automatic subtitling with speech recognition. Automatic emotion recognition. Automatic shot listing in audiovisual production. Automatic translation. E-discovery, legal discovery. Hands-free computing, speech recognition computer user interface. Home automation. Interactive voice response. Mobile telephony, including mobile email. Multimodal interaction. Real-time captioning. Robotics. Security, including usage with other biometric scanners for multi-factor authentication. Speech-to-text, transcription of speech into text, real-time video captioning, court reporting. Telematics, e.g. vehicle navigation systems. Transcription, digital speech-to-text. Video games, with Tom Clancy's End War and Lifeline as working examples. Virtual assistant, e.g. Apple Siri. The performance of speech recognition systems is usually evaluated in terms of accuracy and speed. Accuracy is usually rated with word error rate, WER, whereas speed is measured with the real-time factor. Other measures of accuracy include single word error rate, SWER, and command success rate, CSR. Speech recognition by machine is a very complex problem, however. Vocalizations vary in terms of accent, pronunciation, articulation, roughness, nasality, pitch, volume, and speed. Speech is distorted by a background noise and echoes, electrical characteristics. Accuracy of speech recognition may vary with the following: vocabulary size and CONF usability. Speaker dependence versus independence. Isolated, discontinuous or continuous speech. Task and language constraints. Read versus spontaneous speech. Adverse conditions. As mentioned earlier in this article, the accuracy of speech recognition may vary depending on the following factors: Error rates increase as the vocabulary size grows. E.g., the 10 digits 0 to 9 can be recognized essentially perfectly, but vocabulary sizes of 200, 5,000, or 100,000 may have error rates of 3%, 7%, or 45% respectively. Vocabulary is hard to recognize if it contains confusing letters. E.g., the 26 letters of the English alphabet are difficult to discriminate because they are confusing words, most notoriously, the E set, B, C, D, E, G, P, T, V, Z. When Z is pronounced Z rather than Z depending on the English region, an 8% error rate is considered good for this vocabulary. Speaker dependence versus independence. A speaker-dependent system is intended for use by a single speaker. A speaker-independent system is intended for use by any speaker, more difficult. Isolated, discontinuous or continuous speech. With isolated speech, single words are used, therefore it becomes easier to recognize the speech. With discontinuous speech, full sentences separated by silence are used, therefore it becomes easier to recognize the speech as well as with isolated speech. With continuous speech, naturally spoken sentences are used, therefore it becomes harder to recognize the speech, different from both isolated and discontinuous speech. Task and language constraints. E.g., querying application may dismiss the hypothesis the apple is red. E.g., constraints may be semantic, rejecting the apple is angry. E.g., syntactic, rejecting red is apple. The constraints are often represented by grammar. Read vs. Spontaneous speech. When a person reads, it's usually in a context that has been previously prepared, but when a person uses spontaneous speech, it is difficult to recognize the speech because of the disfluencies, like and false starts, incomplete sentences, stuttering, coughing, and laughter, and limited vocabulary. Adverse conditions, environmental noise, e.g., noise in a car or a factory. Acoustical distortions, e.g., echoes, room acoustics. Speech recognition is a multi-leveled pattern recognition task. Acoustical signals are structured into a hierarchy of units, e.g., phonemes, words, phrases, and sentences. Each level provides additional constraints, e.g., known word pronunciations or legal word sequences, which can compensate for errors or uncertainties at a lower level. This hierarchy of constraints is exploited by combining decisions probabilistically at all lower levels, and making more deterministic decisions only at the highest level. Speech recognition by a machine is a process broken into several phases. Computationally, it is a problem in which a sound pattern has to be recognized or classified into a category that represents a meaning to a human. Every acoustic signal can be broken into smaller, more basic subsignals. As the more complex sound signal is broken into the smaller subsounds, different levels are created, where at the top level we have complex sounds, which are made of simpler sounds on the lower level, and going to lower levels, even more, we create more basic and shorter and simpler sounds. At the lowest level, where the sounds are the most fundamental, a machine would check for simple and more probabilistic rules of what sound should represent. Once these sounds are put together into more complex sounds on upper level, a new set of more deterministic rules should predict what the new complex sound should represent. The most upper level of a deterministic rule should figure out the meaning of complex expressions. In order to expand our knowledge about speech recognition, we need to take into consideration neural networks. There are 4 steps of neural network approaches. Digitize the speech that we want to recognize. For telephone speech, the sampling rate is 8,000 samples per second. Compute features of spectral domain of the speech, with Fourier transform. Computed every 10 milliseconds, with one 10 milliseconds section called a frame. Analysis of 4-step neural network approaches can be explained by further information. Sound is produced by air, or some other medium, vibration, which we register by ears, but machines by receivers. Basic sound creates a wave which has 2 descriptions: amplitude, how strong is it, and frequency, how often it vibrates per second. Accuracy can be computed with the help of word error rate, WER. Word error rate can be calculated by aligning the recognized word and referenced word using dynamic string alignment. The problem may occur while computing the word error rate due to the difference between the sequence lengths of the recognized word and referenced word. Speech recognition can become a means of attack, theft, or accidental operation. For example, activation words like Alexa spoken in an audio or video broadcast can cause devices in homes and offices to start listening for input inappropriately, or possibly take an unwanted action. Voice-controlled devices are also accessible to visitors to the building, or even those outside the building if they can be heard inside. Attackers may be able to gain access to personal information, like calendar, address book contents, private messages, and documents. They may also be able to impersonate the user to send messages or make online purchases. 2 attacks have been demonstrated that use artificial sounds. One transmits ultrasound and attempt to send commands without nearby people noticing. The other adds small, inaudible distortions to other speech or music that are specially crafted to confuse the specific speech recognition system into recognizing music as speech, or to make what sounds like one command to a human sound like a different command to the system. Popular speech recognition conferences held each year or two include Speech TEK and Speech TEK Europe, ICASP, Interspeech/Eurospeech, and the IEEE ASRU. Conferences in the field of natural language processing, such as ACL, NACL, IMLP, and HLT, are beginning to include papers on speech processing. Important journals include the IEEE Transactions on Speech and Audio Processing, later renamed IEEE Transactions on Audio, Speech and Language Processing, and since Sep 2014 renamed IEEE/ACM Transactions on Audio, Speech and Language Processing after merging with an ACM publication, Computer Speech and Language, and Speech Communication. Books like Fundamentals of Speech Recognition by Lawrence Robiner can be useful to acquire basic knowledge but may not be fully up to date, 1993. Another good source can be Statistical Methods for Speech Recognition by Frederick Jelinek and Spoken Language Processing, 2001, by Suidong Huang etc., Computer Speech, by Manfred R. Schroeder, 2nd edition published in 2004, and Speech Processing, a dynamic and optimization-oriented approach published in 2003 by Li Deng and Doug O'Shaughnessy. The updated textbook Speech and Language Processing, 2008, by Jurowski and Martin presents the basics and the state-of-the-art for ASR. Speaker recognition also uses the same features, most of the same front-end processing, and classification techniques as is done in speech recognition. A comprehensive textbook, Fundamentals of Speaker Recognition, is an in-depth source for up-to-date details on the theory and practice. A good insight into the techniques used in the best modern systems can be gained by paying attention to government-sponsored evaluations such as those organized by DARPA. The largest speech recognition-related project ongoing as of 2007 is the GALE project, which involves both speech recognition and translation components. A good and accessible introduction to speech recognition technology and its history is provided by the general audience book The Voice in the Machine. Building Computers That Understand Speech by Roberto Piroxini, 2012. The most recent book on speech recognition is Automatic Speech Recognition, a Deep Learning Approach, publisher, Springer, written by Microsoft researchers Dun Deng and published near the end of 2014, with highly mathematically oriented technical detail on how deep learning methods are derived and implemented in modern speech recognition systems based on DNNs and related deep learning methods. A related book, published earlier in 2014, Deep Learning, Methods and Applications by L. Deng and Du, provides a less technical but more methodology-focused overview of DNN-based speech recognition during 2009 to 2014, placed within the more general context of deep learning applications including not only speech recognition but also image recognition, natural language processing, information retrieval, multimodal processing, and multitask learning. In terms of freely available resources, Carnegie Mellon University's Sphinx Toolkit is one place to start to both learn about speech recognition and to start experimenting. Another resource, free but copyrighted, is the HTK book, and the accompanying HTK Toolkit. For more recent and state-of-the-art techniques, Kaldi Toolkit can be used. In 2017 Mozilla launched the open-source project called Common Voice to gather big database of voices that would help build free speech recognition project DeepSpeech, available free at GitHub, using Google's open-source platform TensorFlow. When Mozilla redirected funding away from the project in 2020, it was forked by its original developers as Coqui STT using the same open-source license. Google Board supports speech recognition on all Android applications. It can be activated through the microphone icon. The commercial cloud-based speech recognition APIs are broadly available. Thank you for watching this video.